Welcome students. In continuation with our previous lecture, we were discussing about examples of direct titrations, wherein we had discussed about the lead tartrate complex, in which tartrate is called the auxiliary complex former. In the direct titration of manganese 2 using eriochrome black tea, the aerial oxidation of manganese 2 can occur. The oxidation of manganese 2 to manganese 4 results in the formation of a brown precipitate which does not react with EDTA. Also, manganese in its higher oxidation state forms a very stable complex with EBT and thus blocks the indicator. This oxidation is prevented by adding a reducing agent like ascorbic acid or hydroxylamine hydrochloride. So, in certain cases where aerial oxidation of the metal ion takes place, then in that case some other example or some other reagent needs to be added. Calcium can be titrated using muroxide as the indicator. So, apart from eriochrome black tea, calcium can also be titrated using muroxide. However, the endpoint is not very sharp. The addition of a masking agent like naphthol green B, it is a non-chelating dye, it helps. The color changes from dirty red to clear blue. The pH needed for the working of the indicator is 12. At this pH, magnesium, if present along with calcium, as in case of hard water, precipitates as magnesium hydroxide, because magnesium forms its hydroxide at a high pH and does not interfere in the estimation of calcium. So, there is an advantage if we use the masking agent, that is naphthol green B, wherein the pH which is needed for the working of the indicator, which is 12, that is the muroxide indicator, and it automatically at that particular pH magnesium precipitates as magnesium hydroxide and calcium can give a color change towards the endpoint using muroxide as the indicator, and this goes very well with hard water wherein both calcium and magnesium are present together and only calcium has to be estimated. Copper can be estimated or titrated using muroxide as the indicator. In this, an excess of the buffer should be avoided, since the copper indicator complex gets decomposed in the presence of a large concentration of ammonia because of the formation of soluble tetramine complex of copper. We have already discussed that copper cannot be titrated with ammonia because copper ammonia complex, which is termed as the tetramine complex of copper, follows a stepwise reaction, a 4-step reaction, and therefore it is a very tedious reaction in which direct titration or a complexometric titration cannot be performed. But when copper is titrated with EDTA, as in a complexometric titration using muroxide as the indicator, care should be taken that the pH of the solution should not be very high, since the copper indicator complex, that is the copper muroxide complex which forms, will decompose at a very high pH, which is there in case of excess of buffer. The titration of nickel with muroxide is slow at room temperature. So, the titration can be performed in slightly warm solution of the metal ion, and warming the solution speeds up the reaction, as in case of titration of magnesium also with EDTA. The titration of bismuth is done using pyrocatechol violet as the indicator. We have already seen the structure of pyrocatechol violet earlier. Bismuth salts have a tendency to hydrolyze in the presence of alkaline medium. So, the solution needs to be neutralized to a proper pH before the start of the titration, and the color change in this titration is from blue to yellow, that is bismuth pyrocatechol violet complex, that is bismuth indicator complex, is blue in color, which on titration wherein the bismuth EDTA complex forms is and pyrocatechol violet is set free in the solution, the color changes to yellow due to the free indicator. Copper can be estimated complexometrically using PAN as the indicator. PAN is a short form of polyacrylonitrile. Copper EDTA complexes are highly stable and hence the titration of copper 2 is feasible even in acetic acid medium. Under this condition, alkaline earth metals and if manganese present in small amounts does not interfere in this titration. However, the reaction between copper PAN and EDTA, that is a copper indicator wherein the indicator is PAN and EDTA, is slow at room temperature due to the insolubility of the copper PAN complex in aqueous solution. This reaction can be made to proceed fast by either boiling the solution or by the addition of an organic solvent. Ferric ions or iron 3 can be titrated with EDTA using potassium thiocyanate KSEN as the complexing agent. This titration is to be performed at a pH of 2 to 3 because the indicator gives a color change at a pH of 2 to 3. At lower pH, some of the indicator itself complexes and iron EDTA complex is highly dissociated. At higher pH, Fe3 tends to hydrolyze. That means at a lower pH below 2 to 3 and at a higher pH beyond 3 to 4. The conditions which are required for the titration of iron 3 with EDTA: iron 3 reacts slowly with EDTA, so the titration must be performed slowly or at elevated temperatures but not above 40 to 50 degrees C to avoid hydrolysis. The color change on this titration is from red to yellow or colorless towards the end point. Back titration in this case, in the previous case which we have just discussed, gives better results, but direct titration is advantageous in terms of speed and higher selectivity. Red color is due to the formation of ferric thiocyanate complex in ammoniacal medium, whereas yellow color is due to the formation of the iron EDTA complex. So, in this case, when we are talking about a red to yellow color change, then here the red color is due to the complex of iron and the indicator, whereas the yellow color is due to the iron EDTA complex, in contrast with the cases where we were discussing about the zinc complexes with EBT or magnesium complexes with EBT. In those cases, the color change was due to the metal indicator changing to the free indicator. Here the color change is due to the metal indicator changing to the metal in EDTA complex. Nickel can also be titrated in terms of back titration using PAN or polyacrylonitrile as the indicator, and the structure of PAN is given as in the adjoining figure. Nickel can be back titrated with copper as a metal. When we talk about back titrations, then they are performed with one metal being back titrated against another metal ion. Nickel forms a very good deep colored complex with PAN, but the reaction is very slow and a direct titration is impossible because nickel completely blocks the indicator. That is, it completely blocks the indicator means it completely blocks the action of the indicator. Hence, a back titration procedure has to be applied. In this procedure, 10 ml of nickel solution is taken in a conical flask and EDTA is added in excess. After that, 5 ml of buffer is added and 3 drops of the indicator, which is PAN. The solution upon dilution to 100 ml becomes yellow. This solution is titrated with copper solution from the burette till the color changes to violet. So hence, as we can see over here, that the titration is not being performed with EDTA from the burette. Instead, in the burette we have taken another metal ion solution and the titration is being performed with the metal ion solution, and the EDTA is taken as a complex with the metal ion, which has to be estimated. Another example of back titration is the estimation of aluminium using ferrocyanide benzidine as the indicator, and this aluminium over here is back titrated using zinc in the burette. So at a pH of 5, benzidine is not oxidized by ferrocyanide if a small concentration of ferrocyanide is present. The aluminium EDTA complex forms very slowly. If EDTA is back titrated with zinc, since the formation of zinc ferrocyanide is a fast reaction, there is a fast color change at the equivalence point. Thus, a back titration procedure is applied for obtaining a sharp end point. So, if the color change towards the end point is fast, then the color change will not be very sharp. It will be a sluggish color change, and once the color change is not sharp, then one cannot exactly determine that how much amount of a particular metal ion has been used for back titration of the estimation of a particular metal ion. So, if an excess of EDTA is back titrated with zinc solution using ferrocyanide benzidine as the indicator, then many metals including aluminium, iron and lead can be estimated. The aluminium EDTA complex in this case forms very slowly. The hydrolysis of uncomplexed aluminium occurs, which results in a slow reaction. So, the reason why aluminium EDTA complex forms very slowly is the hydrolysis of uncomplexed aluminium. In order to avoid hydrolysis, the aluminium solution is in acidic form, which needs to be neutralized after the addition of EDTA. This hydrolysis occurs because of the slow rate of complexing. During neutralization, there remains some uncomplexed aluminium. Local excess of alkali occurs by the addition of each drop of ammonia or sodium hydroxide, which causes the hydrolysis of uncomplexed aluminium. If the pH is increased, aluminium gets released from its EDTA complex. Aluminium forms its hydroxo complexes, which do not react with EDTA. Hence, all of the aluminium needs to be converted into EDTA complex before the back titration starts. The addition of a large excess of EDTA, that is to speed up the complex formation, neutralization to prevent the formation of hydroxo complexes, a long standing period before the start of back titration to prevent sufficient time for complex formation, and heating the solution to increase the rate of complex formation are some of the conditions necessary to fulfill the requirement of converting all aluminium into EDTA complex before being back titrated with zinc. So, we all know now in this case that we need to add a large excess of EDTA. We need to first neutralize the solution, and that neutralization is to prevent the formation of aluminium hydroxo complex, and we need to provide a long standing period for the solution before the start of the titration, and that standing period is provided to enable complex formation easily, and also we need to heat the solution to increase the speed of the titration, and then only the titration of aluminium EDTA complex can be performed with zinc. Back titration should be done in cold solution because zinc ferrocyanide is soluble in hot solution. As we remember that ferrocyanide is being used as the indicator, so zinc, which is used in the burette, can form the zinc ferrocyanide complex, which will be soluble in hot solution. So, therefore, this titration of aluminium EDTA complex with zinc needs to be performed in cold. and the color change during this titration is pink to blue towards the end point. In this procedure, 10 ml of aluminum solution is taken in a conical flask and excess of EDTA is added. That excess is definitely a known volume. Then a few drops of phenolphthalein indicator is added and then NaOH till a pink color is obtained. The reason for adding phenolphthalein is that upon adding NaOH, we will come to know that how much the solution has been utilized, and tight one drop in excess will result in the color change of the phenolphthalein indicator to pink, as is evident in case of acid base titrations. As we know, phenolphthalein is pink in basic medium and colorless in acidic medium. Then 10 ml of buffer is added and the solution is boiled for 2 minutes. This solution is then cooled and diluted. After that, 1 ml of very ferrocyanide solution is added along with 3 to 4 drops of benzidine solution. This solution is then back titrated with zinc with shaking till the blue color appears. As we know, the endpoint which we have just discussed is from pink to blue. Now we have another set of titrations in complexometry which are termed as replacement titrations. And these titrations are to be performed for various metal ions wherein the metal ion indicator complex is weak. For example, in the case of titration of calcium by magnesium EDTA complex and EBT as the indicator. Now, a point to be noted over here is that this replacement titration needs to be done for calcium if we are using eriochrome black tea as the indicator, because the calcium indicator complex here is weak. If in case of eriochrome black tea, some other indicator specific for calcium, for example calcon, is used, then replacement titrations need not be carried out. Calcium can be directly titrated with EDTA using calcon as the indicator. So, coming back to replacement titrations, calcium EBT complex is weak. So, upon titration with EDTA, the complex breaks immediately on adding a very small amount of EDTA. A direct titration therefore is not possible using EBT. If magnesium is present in the solution, as in case of hard water or as in case of a mixture of calcium and magnesium in a particular solution, then calcium is complexed with EBT first and then magnesium. So, the reaction of magnesium with EBT is the one which gives the end point. The principle behind this is that the stability of the calcium indicator, that is the calcium EBT complex, is lesser than the stability of the magnesium EBT complex. This is important in cases where hardness of water needs to be determined. So, therefore, in a particular case of titration of calcium with eriochrome black tea, since calcium eriochrome black tea complex is weaker than magnesium eriochrome black tea complex, so magnesium needs to be added for the titration of a calcium EBT complex, because the endpoint, as we have just seen, will be determined by the magnesium EBT complex once it breaks with EDTA. However, in cases where magnesium is not present along with calcium, it may be added externally as magnesium EDTA complex, so that calcium can be titrated via partial replacement titration. So, in this case, to a 10 ml of calcium ion solution in a conical flask, 5 ml of magnesium EDTA solution is added. This is an example which is given in case where magnesium is not present along with calcium. That means if we take water sample, a hard water sample, in that case calcium and magnesium both are present, but in cases where magnesium is absent, then magnesium EDTA complex needs to be added. Then 10 ml of buffer needs to be added again to maintain the pH, and a pinch of the indicator EBT is added. This solution is then heated and then titrated with EDTA till the color changes from red to blue. This color change is the same as in case of individual titrations of zinc with EDTA or magnesium with EDTA, or as in this case calcium with EDTA. The red color, as we all know, is due to the formation of the metal indicator complex, and the blue color is due to the formation or the release rather of the free indicator after the metal ions have exhausted and they have formed a complex with EDTA. 1 ml of 0.01 molar EDTA will be equal to 0.4 milligram calcium, and by the series of calculations we can determine how much amount of calcium ions are present in a given sample, whether it is a water sample, whether it is a given solution. Another example of a replacement titration is the titration of mercury ions or mercurous by magnesium EDTA complex and using iriochrome black tea as the indicator. In this case, 10 ml of mercury solution is taken in a conical flask. If this solution is acidic, then 2 drops of methyl red indicator are added, and then the solution is neutralized with NaOH till the color of the solution changes to yellow. The methyl red indicator is again telling us whether the solution is acidic or alkaline, as methyl red is red in acidic conditions and its color changes to yellow in alkaline solution. So, after neutralization, 1 drop excess of NaOH which is added gives the color change of the indicator to yellow, which indicates that the solution has been neutralized fully. After that, 10 ml of the buffer is added along with 5 ml of the magnesium EDTA solution. Then iriochrome black tea indicator is added and the solution is titrated with EDTA till the color changes again from red to blue. Again the same color change which we have seen for the previous titrations. And 1 ml of 0.01 molar EDTA will be equal to 2 grams of mercurous ions in the solution. Next is the titration of lead, another example of a replacement titration by copper EDTA complex using PAN as the indicator. The titration of lead takes place in acidic solution, since error due to alkaline earth metals can be avoided as they do not complex with EDTA in acidic medium. And if an acidic medium is created, then the titration of lead takes place smoothly. Hence, a replacement titration involving copper EDTA PAN system is done. Lead can also be titrated directly using xylene oil orange as the indicator. So, if lead has to be determined by a replacement titration, then it is titrated using copper EDTA complex and PAN or polyacrylonitrile as the indicator, and if it needs to be titrated directly, then xylene oil orange can be used as the indicator for its particular titration. Thank you so much.